Hello. Okay, so let's continue with the Hoeffding lemma. Actually, I will have to restart it. So remember, we basically the Hoeffding lemma is an attempt to upper bound the moment generating function of a specific class of random variables that are useful in applications. And so those are basically random variables that are zero mean, that are almost surely in the range from a to b, where a is a negative number and b is a positive number. Okay, so we want to upper bound the moment generating function, which is given by this expectation with t belongs to r. Remember that basically the moment generating function is finite, for typically a subset of r. Okay, it can be finite for all r, but it can be finite just when t is equal to 0. The moment generating function at t equals 0 is 1, or it may be finite in some range, like we did last time, the exponential random variable. The moment generating function was finite from -infinity to lambda, where lambda basically is the parameter of the exponential random variable. Now, for those guys, because the random variable belongs to a finite interval almost surely, then the moment generating function is basically is finite for every real number, right? Because like the moment generating function here is like you can upper bound it by basically e to the absolute t, and then the maximum of the absolute value of a, the absolute value of b, right? So for a finite t, this thing will be finite in our case here. Typically, troubles are for random variables that extend from -infinity to infinity. Okay, so the random variable is between a and b. Okay, so x is living here, but rather than using x, we can use lambda, and lambda is between 0 and 1, and we can write down x as a convex combination of a and b. And so a convex combination is basically a non-negative linear combination in which the coefficients sum to 1. So I can write x as lambda a plus 1 minus lambda b. Okay, so basically those guys are non-negative, and their sum, lambda plus 1 minus lambda is 1. Okay, so generally a convex combination of numbers. So if you have a number zi, a convex, this is called a convex combination. A convex combination if basically those alpha i's are non-negative and the sum of the alpha i's is equal to 1. Okay, and this means basically that x is somewhere between a and b. If lambda is 1, x is a. If lambda is 0, x is b. If lambda is 0.5, x is the midpoint between a and b, and so forth. Okay, so this is x in terms of lambda. You can take expectation of both sides. We know that x is a zero mean random variable, so we can obtain the expected value of lambda. Then we can exploit the convexity of the exponential function, e to the tx. So now forget that x is a random variable, just deal with it as a real number. Okay, so what we have here is basically e to the lambda. Okay, so we replace x by lambda a plus 1 minus lambda b, and so this thing becomes e to the lambda ta plus 1 minus lambda tb. And because the exponential function is convex, by definition, this is less than or equal to lambda e to the ta plus 1 minus lambda e to the tb. And how do we know that the exponential function is convex? Well, I mean, because it's a differentiable function, we can differentiate twice. The second derivative will be non-negative, and so this means that basically the function is convex. Then we can now remember that x and lambda are basically random variables. We take the expectation of both sides. This guy becomes the moment generating function, and here a is a constant, b is a constant, t is a constant, and so we take the expectation of lambda. We have a formula for it here, and so we just plug in the expected value of lambda. And then this thing here, basically we will write it as e to the g of t. Okay, so you have something written as e to the g of t. So what is this g of t? So g of t is basically the natural logarithm of this quantity here. Okay, so g of t is the natural logarithm, and this quantity here is basically positive. I mean, there is a minus sign, but don't forget that a itself is a negative number. Then, as we did last time, you can basically sort of investigate function g. The target is, or the goal is basically the second order Taylor polynomial for g of t, polynomial for g of t. Okay, and so what we do is that we take g of t at 0, and we will do it about 0. So it's a second order Taylor polynomial about 0. Okay, so g of 0, check it's 0. First derivative, you differentiate with respect to t. Normal rules, nothing else. You basically set t equals 0, you get also 0. Then you do the second differentiation, and you basically get this thing here. Okay, and the Taylor expression for a function that is twice differentiable, like our guy here, g of t is equal to g of 0, okay, plus the first derivative evaluated at 0 multiplied by t, plus 1/2 of t squared, and then we have the second derivative evaluated at some number between 0 and t. So here we have equality, okay? We have equality, so here we need to use like zeta, where zeta is a number between 0 and t, okay? This guy is 0, this guy is 0. Now, this is the second derivative. So what we will do is basically that we will upper bound g of t by upper bounding its second derivative. Okay, so this is the second derivative. It's not a so nice function. If you put t equals zeta, you will get something that looks, you know, a bit scary. But you can actually upper bound this thing nicely using the arithmetic mean geometric mean inequality. And so here are our two positive quantities, minus a e to the tb, that's one of them, b e to the ta, that's another of them, and the arithmetic mean geometric mean inequality tells you that basically if you have two you know, alpha beta that are positive, then the square root, which is basically, so this thing is the geometric mean of alpha and beta, is upper bounded by the arithmetic mean with equality if and only if these two numbers are equal. Okay, so basically the product of these two positive quantities will be upper bounded by the square of the arithmetic mean, which is the sum divided by 2. Okay, so if you now go to the formula for the second derivative, so this thing here, you know, this, these two terms here, by applying the arithmetic mean geometric mean inequality, is upper bounded by b e to the ta minus a e to the tb over 2 squared, and then this guy in the numerator squared is the same guy in the denominator, so by, and then you have 1 over 4, okay, which will remain from here. So basically we can upper bound the second derivative by something that does not depend on t, that does not depend on zeta. It is just a function of those endpoints of the interval, you know, a and b. Right? Remember that x belongs to the interval a to b almost surely. Okay, so things here depend just on these two constants, a and b. And so what we will do is that we will take we'll take g of t, and using, you know, the Taylor expression, basically this is its value, but we will use an upper bound, and this will be the upper bound. It depends on b and a. For the second derivative, and then we have t squared because this is the, you know, it's basically the quadratic term in the Taylor expansion. Then that's it. So basically, remember from above that mx of t is less than or equal to. So we already used an inequality upstairs, basically when we exploited the convexity of the exponential function, and so this guy was like less than e to the gt, but this gt is less than 1/8 b minus a squared t squared, and so the moment generating function of this class of random variables is less than or equal to 1/8 b minus a squared. Okay, so this is the length of the interval, right? Because the random variable is from a to b, and basically a is negative, so b minus a is like, you know, b minus a is like b plus minus a here, and gives you basically this this length, the length of the interval on which basically the random variable is defined, et squared. So this is an upper bound. It seems like an exercise. Okay, so what is the issue? So this is like sort of a lemma that we will need later when we study the Hoeffding inequality. So the Hoeffding inequality is an inequality. It's a probability inequality, and it uses a technique called the Chernow bound that we will study later. And in the technique, the moment generating function will appear, and sometimes we can use it directly, but sometimes we upper bound the moment generating function. So this result will be handy when we study basically the Chernow bound and specifically the Hoeffding inequality. Okay, now sometimes we use the log moment generating function, which means that you just take the moment generating function and apply to it the natural logarithm. Not a big deal. And remember that if 0 is interior to the domain of the moment generating function, so basically if the moment generating function is finite in some neighborhood about 0, that's basically where the moment generating function can do wonders. Basically, in that case, you are sure that your random variable has finite moments of any order. The moment generating function will be infinitely differentiable, and the derivatives basically can be used directly to obtain the moments. Okay, so it's differentiable. So if you define small mx of t as the natural logarithm of big mx of t, now suppose that you want like to see how are, what are the derivatives of this log moment generating function if we evaluate those derivatives at 0. So you just, basically write mx of t is then mx of t, differentiate both sides. Now we are sure that this guy actually is differentiable as many times as you wish, okay? And using this, you can show that the first derivative of small mx of t, which is the log moment generating function evaluated at 0, is also the first moment of the random variable. If you differentiate twice, okay, so you basically differentiate this thing here, applying the quotient rule for differentiation, and then plug in t equals 0. Now this guy here is equal to the variance of x. Remember that if we take x, the big M, the moment generating function, if we differentiate it twice and then put t equals 0, this will give us the second moment. Okay, will give us the second moment. And generally, if we put this 2 as n, we will get an n here. Now, for basically small m, which is the log moment generating function, basically if you put 1, you get x, the first moment. If you put 2, you get the variance. Okay. While the moment generating function itself will give you the second moment. And of course, these two guys are equal if it happens that your random variable is 0 p. Now, the moment generating function, remember that if it was finite at t1 less than t2, then it was finite at any number between t1 and t2, and it was convex. We also have convexity for the log moment generating function, and we can prove it using Holder's inequality. So let's actually show convexity directly using the definition of convexity. So pick a lambda between 0 and 1 and investigate what is small mx of lambda t1 plus 1 minus lambda t2. By definition, this is the natural logarithm of the moment generating function, and the moment generating function is expectation tx, and now t is basically this thing here, x. Okay, so now separate this exponential into e to the t1 x lambda, e to the t2 x1 minus lambda. Okay, so we have the exponential of basically two positive quantities. Okay, so if a and b are positive, basically Holder's inequality tells you that this expectation is upper bounded by, then you can take a to the b. Okay, so those are positive, a to the b, and then 1 over b, and then a expectation b to the q, 1 over q. P and q are not arbitrary. We have 1 over p plus 1 over q equal unity, equal 1. Okay, so now we have we have this exponential we have this expectation of a product. Then we can basically separate it into two expectations via the Holder inequality like this. Okay, and then if you apply the Holder inequality, this thing will be raised to the power p, and so it will be e to the t1 x lambda b. Okay, and what you can do is that you can choose. So basically p and q are basically greater than or equal to 1, q greater than or equal to 1. So what we can do here is choose b to be 1 over lambda. Okay, so strategically, what we will do after applying Holder inequality for a general p, we'll say, oh, we will do this particular choice for p. We will choose basically p to be 1 over lambda, so that this thing here is equal to 1. And once you fix p, because you have this relationship here, you get q. If you say p is equal to 1 over lambda, that's it for you. Then obtain q as a function of lambda, and it will be 1 over 1 minus lambda. Okay, so you substitute. So now you know b, and after choosing certain values for p and q, you basically plug in, and then this is what you get. Okay, so you will have this first expectation raised to the power lambda, second expectation 1 minus lambda. Basically, the logarithm of a product is a sum of logarithms, and then the logarithm of something raised to the power, basically the power can come outside here. And then basically, what is this thing? So what is this thing, inside the logarithm? It's expectation e to the t1x. It's the moment generating function at t1. This is the moment generating function at t2. Then we take the logarithm. So this is a small mx of t1. This is a small mx of t2. And then we have lambda here, 1 minus lambda there. So using the Holder inequality, we proved that this small m evaluated at this point is less than or equal to lambda, this guy here plus this guy there. And that's exactly the definition of convexity. And so mx of t is a convex function. Okay, again, something that is relevant, because typically, like the moment generating function, the log moment generating function can be involved in optimization problems, and it is nice to know that it is convex. It has implications when this thing is involved in optimization. And optimization will come in the Chernoff bound, as we will see later. Okay. Now, to the lovely function, the characteristic function. So we talked about it in a previous tutorial session. It looks like the moment generating function, but rather than t, we have iu. I is the square root of -1, and u is a real parameter. At 0, it is 1. What is the advantage of the characteristic function? As we said earlier, basically the magnitude is always less than or equal to 1. This expectation here is always finite. Okay, it's always finite for every u that is in R. Okay, now you can show that basically the conjugate of the characteristic function is basically the characteristic function with u replaced by -u. What is the characteristic function of ax? Okay, so x is scaled by a. Well, apply the definition, expectation e to the iu ax. And then you can think of this as e to the I between brackets u ax. And so this thing is like the characteristic function of random variable x evaluated at ua, right? So keep this in mind. If we have phi and then a constant x of u, we can take this constant inside. This is phi x of au. Okay, so keep this in mind. And for the special case, what if a is minus 1? If a is -1, then phi of minus x is phi x of minus u. And because of the Hermitian symmetry, this property is called the Hermitian symmetry, basically phi x of minus u is equal to phi x conjugate of u. So phi of minus x of u, again, depending on what you are doing, then you can set it as phi x of minus u or phi x of u conjugate. Now, we have, like for the moment generating function, it's the same idea. If we have a bunch of independent random variables, basically the characteristic function of the sum will be product of characteristic functions. Characteristic function of a sum becomes a product. Okay, and if all those guys are distributed as x, or like all of them are identically distributed, then basically this is like taking the characteristic function of one of them. All of them will be the same now, because this expectation will be the same if the guys are identically distributed, and so this will be the characteristic function raised to the power n in the i.i.d. case. If they are just independent, then we have a product. Still, it is something that is powerful, and we will actually see why is this thing powerful. We can use it like to prove things like the central limit theorem. Okay, and sometimes we have like a random variable defined as such. So we have a random variable x. It's x1 with probability b1, x2 with probability b2, and x3 with probability b3, and so on and so forth. So we have a random variable. So we have like a bunch, a sequence of random variables, and then we define a random variable that can be equal to the first guy with probability p1, the second guy with probability b2, the third guy with probability b3, and so on and so forth. Suppose that those probabilities are between 0 and 1, and their sum, of course, they are probabilities, and this basically to exhaust all possibilities, basically the summation is equal to 1. So what is our goal here, or the interest, is basically what is the characteristic function of this guy, defined in such a way. Definitely this characteristic function is related to the characteristic function of x1, the characteristic function of x2, x3, and so forth. Okay, so let's define a discrete random variable z with a PMF basically that is these probabilities, right? Those probabilities are like a PMF. Like they are basically numbers between 0 and 1, and their sum is equal to 1. Okay, so basically we will define a random variable z such that the probability that z is equal to k, this probability is the number p sub k, like this. Okay, now given that z is equal to k, so if z is equal to k, then x is equal to xk. So basically, this is how we define the random variable z. So z basically is a random variable that tells you which of those x's is this x. Okay, so again, there are random variables x1, x2, x3, x4, x5, x, and so on. So we have this sequence, and then we have x. So x is equal to one of the guys. And so what we basically do is say that there is another random variable z, and z, if z is 1, then x is x1. If z is 2, then x is x2. If z is 3, then x is x3, and so on and so forth. Okay, so given that z is equal to k, x is equal to xk. So it's like random variable z is like the selector that will tell you which of those x's is actually this big X. Okay, so again, don't forget, what is the goal? The goal is, so what is the characteristic function of this guy here? So definition, expectation e to the minus ux. Then, so here again, iterated expectations can be very helpful. So an expectation like this can be written as an expectation of x given z, and then an outer expectation with respect to z. Remember the iterated expectation, you have an expectation, let's say you want it with respect to a, then if the expectation is a finite number, then basically this expectation you can take it with a given b, and then an outer expectation with respect to b. So iterated expectation is very useful. So what you can do is you condition on z, and then after conditioning on z, then basically you take the expectation with respect to z. Okay, so once you fix z, so here z is fixed. So here, in this guy here, z is fixed. So let's say z is equal to 7. So what is the moment generating function, the characteristic function if z is 7? Well, what does it mean that z is 7? If z is 7, then x is x sub 7. X is x7. Because again, if z is k, then x is equal to xk. So if z is equal to 7, okay, then x is equal to x7, and the characteristic function will be the characteristic function of the random variable x7. Okay, so the inner expectation is phi of xz of u, which means that if z is 1, this is the characteristic function of x1. If z is 2, this is the characteristic function of x2. If z is 3, it's the characteristic function of x3. Okay, why? Because if z is equal to k, then x is equal to xk. And so, are we done? Not yet, because this is the inner expectation, assuming like z is like a constant, it's 7. But it is not. Well, Z, it can be 1 or 2 or 3 or 4 or 5 with basically those probabilities here. And so we need an outer expectation. Now the outer expectation with respect to Z. Lotus. Okay, so Lotus tells you what is this expectation of a function of Z. Well, write down. So this is the probability that Z is equal to K, and then write down the function with Z equal K. Lotus, nothing else. Okay, so this is a function of random variable Z. Okay, so take the probability that Z is equal to K and multiply it by the function evaluated at basically this value of Z, which is K. Okay, and so basically we get this nice result. So what is the probability that Z is equal to K? It's PK. And so the characteristic function of X that is defined in this, apparently funny way, but, it's very useful. Again, like there are several problems in which like X is defined as such. Then, it is summation K from 1 to infinity, BK phi XKU. And those BKs are non-negative and they sum to 1. So so we can say it in words like this. The CF of X in our case is a convex combination of the characteristic functions, the CFs of x1, x2, x3, and so on. And those coefficients in the convex combination are nothing but the probabilities. Bk is the probability that x is equal to x. Okay, so that's like sort of a nice exercise on the characteristic function, but of course there is much more. Before going to the central limit theorem, let's basically, as we did for the moment generating function, and we tried like to relate it to the moments, let's play the same game with the characteristic function. How is the characteristic function related to the moments of a random variable? Okay, so we will use, basically we'll need inequalities. So let me basically try to like explain those inequalities first. So we have here e to the ix. Okay, just think here of x as some constant and u as some. So basically u and x are real. Think of them here as real numbers. Now, what is this thing? If you look at it, it's like Taylor, the Taylor series, but it is truncated, right? It stops at n. Right? So we know that e to the iux, this thing here, is summation, and then we have k from 0 to infinity, then iux to the power k divided by the factorial of k. This is e to the iux. So now what happens if you basically stop at n? Then now, the left and right hand sides, if you stop this one at n, then the left and right hand sides are not the same thing. There will be a difference between them. But it turns out that for this particular function, you can show that there are upper bounds on the magnitude of the difference. Okay? So again, what is this guy? E to the iux. What is this guy? It's the truncated Taylor series. Now it has small n plus 1 terms from 0 to small n. Now we take the magnitude, so that's the difference. The difference because basically for the two guys to be the same, you need to basically push the sum to infinity. Now you stop at n, then there will be an upper bound on the magnitude of the difference. Okay? And so what is this upper bound? So this upper bound has a number of forms, so this is one of them. So the upper bound can be that you pick a parameter delta between 0 and 1. And the upper bound will look something like this. 2 to the 1 minus delta, absolute value of u to the n plus delta. So n is basically, this n here is the same as this n here. Okay? So if you stop here at 3, this will be 3. If you stop here at 4, this will be 4, and so forth. Magnitude xn plus delta, and then the beta function, beta of delta plus 1 comma n. Okay, so the beta function, you can look it up on Wikipedia. Okay, it will not like play a role like in here. Okay, but you can have a look at what this function looks like. And here we have n minus 1 factorial. This is true for every delta between 0 and 1. You can show it, and hence, because it's true for every delta between 0 and 1, then basically this upper bound can be basically replaced by the infimum. Okay, so again, it's like the proof is, if you are interested, proof is using Taylor expansion with the Cauchy integral term. Okay, but we are not interested in the derivation. Okay, you get something like this, and basically you can basically take delta equals 0 or delta equal 1. Okay, so this will be like two special cases, and sometimes we basically, so this one corresponds to delta equals 0, and this term here corresponds to delta equal 1. Now, you can basically do this proof here, but then take expectations. And when you take expectations, what will happen is that this guy here becomes the characteristic function. And then when you take the expectation of this finite sum, the expectation will go and basically attach itself to random variable x. So the difference here, again, between the first line and second line, this is like for real numbers, u and x, but this one, if x is a random variable, then you simply apply the expectation, and you will get here the upper bound. Now, rather than having x's, it will have this expectation with respect to x. Okay, and same story, basically, this corresponds to delta equals 0, this corresponds to delta e. So let's take a special case. Again, like for us here, we don't care about the derivation of those inequalities, but we care about like how to apply them. Okay, so let's take the special case. What if n is 1? What if n is equal to 1? Okay, so if n is 1, then basically, I think I should have a magnitude here. If n is 1, then the magnitude of e to the ix minus, and then we have here two terms only. When n is small n is 0, and when small n is 1, and so when when small k is 0, and then when small k is equal to 1, and so when small k is 0, this is 1, and when small k is 1, this will be iux. Okay, so basically, if n is 1, then we have two terms, k0 and k is equal to 1. If k is 0, we get a 1. If k is 1, we get iux. And so now, if n is equal to 1, then basically we are upper bounding the difference between e to the iux and 1 plus iux. So if we go to this term here, just put small n equals to 1, and you will get this upper bound. And this is if you apply the second inequality, which again is like the first with taking expectation. If n is equal to 2, let's look at this second one, if n is equal to 2. So basically k is equal to 0, 1, and 2. So we have magnitude phi x of u minus, okay. So if k is 0, this is 1. Okay, but if k is 1, this will be I, u, expectation x to the power 1, which is expectation x, over the factorial of 1, which is 1, minus, if k is equal to 2, then we have I squared, so that's minus 1, and then we have u squared, and then we have expectation x squared, and then we have the factorial of 2. Okay, and so those guys will give you these terms here. Now, how do we upper bound this thing? Well, again, you put now n equals 2. And then you have several options. I mean, you can just take this thing at any delta between 0 and 1. You can use the infimum. You can use basically the specific values of delta equals 0 or 1. Okay, if we leave these the upper bound in terms of delta, then basically it will be this expression here with delta. Okay, so left as a general number between 0 and 1, but then small n will be basically replaced by 2. So this 2 here becomes 2 plus delta. This n here becomes n plus delta becomes 2 plus delta. This n here becomes 2, and so forth. So again, it's like an inequality that will be useful for us to basically prove this theorem. So suppose that we have a random variable, and we know that the kth moment is finite. So this is given. We have a random variable x. So random variable x, regardless, it has a characteristic function. It has phi x of u for every real u. Okay, but now let's have more information about x. X has a finite kth moment. In that case, the corresponding characteristic function can be differentiated k times. It can be differentiated k times. And the derivative, the kth derivative, will be given by this expression here. Expectation ix to the k e to the iu. And basically this expectation here is what you get if you are allowed to interchange differentiation and expectation, right? So phi x of u is this expectation, e to the I ux, right? So if you try to differentiate it, okay, let's say you try to differentiate it one time, d by du. You have a problem, which is that you have differentiation, and then we have expectation. And basically, it is not generally true that you can interchange these two. But if we can interchange, if we can swap, basically we can bring this differentiation inside, and this will bring down ix e to the iux, something like this, right? So this is if this swapping is allowed. So here actually we can give a condition that validates this swapping, and this condition is related to the finiteness of generally the kth moment. Okay, so if the kth moment is finite, it's as if you can do this swapping, and then you get this ix to the power k multiplied by e to the ux. And this will be the kth derivative of the characteristic function. And if you evaluate it at 0, you get the kth moment, but then it is multiplied by I to the k. Okay. So I will do the proof for k equals 1. So for k equals 1, our random variable, now it has a finite first moment, so it has a finite first absolute moment. Okay. Now this quantity here, which is expectation ix e to the ix, is it a finite quantity? Let's see. So what is expectation ix e to the ix? If we take the magnitude, then by the triangle inequality, the magnitude of expectation is less than or equal to expectation of magnitude. The magnitude of e to the iux is 1, the magnitude of I is 1, and you are left with the magnitude of x, which is now assumed to be finite, because we are assuming that our random variable has a finite first moment. Okay, so how do we basically show the differentiability of the characteristic function rigorously? So here is the trick. We will basically take phi x of u plus epsilon minus phi x of u divided by epsilon. Note that this thing here is, basically if this thing has a limit, has a finite limit as epsilon goes to 0, this will be basically the definition of differentiability. Okay, so we will take this minus, this is like the candidate derivative. This is what you get if you are allowed to do things like sort of non-rigorously and you interchange differentiation and expectation. So what we will do is that we will investigate the magnitude of the difference between this and that. And we will take the limit as epsilon goes to 0. Okay, now if the limit is 0, what does it mean? So if the limit is 0, so if the limit of a magnitude of a generally complex valued quantity is 0, what does this mean? It means that the thing inside is 0. So if the limit is 0, it means that limit epsilon 0 phi x of u plus epsilon minus phi x of u over epsilon is equal to expectation ix e to the iux. Okay, and what does this mean? It means that this limit exists and is finite and is equal to this quantity here, which means that the characteristic function is differentiable. Okay, and this is actually its derivative. Okay, so this is basically how to do things. So we will take this quantity. Again, this quantity is not a mystery. This quantity is what you examine to check for differentiability. We will take the difference between this quantity and sort of the candidate first derivative, okay? And we'll take the magnitude and then investigate the limit as epsilon goes to 0. As typical, the limit itself will be very hard, maybe impossible to obtain, but we will always make use of the squeeze theorem or the sandwich theorem, right? So basically, if you upper bound this magnitude by something and you show that the limit of the upper bound all goes to 0, then this limit also goes to 0. So that's the game in town, and it's very typical, like, you know, so it's not like something that is, you know, specific here. It's a very, very widely used game, right? So you take the magnitude, and then you basically want to show that this thing is 0. It's tough to like tackle directly. You upper bound, and then you show that the limit of the upper bound is 0. So by the sandwich theorem, it must be the case that this guy here goes to 0, right? Because it's a magnitude, and so this thing is always greater than or equal to 0. So if the limit of the upper bound is 0, we are done. Okay, so basically this is the game plan. Okay, so we start with this quantity, upper bound, show that the limit is 0, so this is 0, and if it's 0, that's it. Then indeed the characteristic function is differentiable, and its first derivative is this guy here. So first order of business, take the characteristic functions and write them down in terms of expectation, and then combine the expectations using the linearity of expectations. So basically this is what we have inside the magnitude. Okay, and then apply our old friend, the triangle inequality. Again, expectation of magnitude of expectation is less than or equal to expectation of magnitude, and for the magnitude, basically you'll get the magnitude of epsilon. Note that here in those three guys you have e to the iux a common factor, and when you apply the magnitude of this thing is 1, and so it will disappear, and you are left with e to the I epsilon x. This guy now is 1 after taking this as a common factor, and this will be minus I epsilon x. Okay? Oh, this looks like what we did upstairs. So this thing is like, you know, you are trying to expand this function using Taylor, and then you stop at the linear term. And so we have an upper bound for this thing. Okay, so it is like this case here. Okay, so the upper bound from the inequality will be the minimum of these two guys. Okay, so this is a place where basically the above inequality will be useful. Okay, so we upper bound by basically these two guys. You know, you can take epsilon as a common factor. So there is a magnitude epsilon here as a common factor. It will eliminate this magnitude epsilon in the denominator, and then we are left with this limit. Okay. So upper bounds, what did we use for upper bounding? Let me review. So triangle inequality. So at one step we used the triangle inequality, and then we used this inequality here. Again, it's a lovely inequality. It's very, you know, it looks very nice. And we basically now have this thing. We are stuck again because, you know, you want to take the limit as epsilon goes to 0, but there is an epsilon here, and between the limit and the epsilon there is an expectation. It's not always valid to interchange expectation and limit. So, but we have here, you know, a theorem that may justify for us, if it's applicable, the dominated convergence theorem. Okay, so let's try to basically apply the dominated convergence theorem. So according to the DCT, what we want to do is that take the thing inside the expectation, take its magnitude, try to upper bound the magnitude by something that does not depend on the variable with respect to which you are taking the limit. Can we do so? Yes, because the minimum of two quantities, the minimum of A and B, is less than or equal to A, and the minimum of A and B is less than or equal to b. The minimum of two quantities is less than or equal to, basically one of them. And so the nice thing is that this minimum, this guy is free from epsilon. So this minimum is upper bounded by the first term, which is free from epsilon. So far, so good. Okay, but the dominated convergence theorem tells you that now you need another thing. You need the upper bound, which does not depend on the variable with respect to which you are taking the limit. You need this upper bound itself. If it is plugged in the expectation, it should give you a finite result. So if we take this thing and apply expectation, well, it gives you finite result if you assume that the random variable has a finite first moment. And so that's the reason that this assumption here is needed. This assumption here is needed because it allows you to apply the dominated convergence theorem. Okay, so the expectation of 2 magnitude x is less than infinity. It's by assumption. It's because we are talking about random variables that have a finite first moment. Okay, so the DCT here is basically alive. And what we can do is that we can interchange the order of limit and expectation. We can basically take the limit inside. Okay, we can take the limit inside. How can we take this limit here? Again, we can use the squeeze or sandwich theorem. The minimum, as I said here, the minimum of two quantities is less than or equal to any of them. And so the minimum of this is less than or equal to, here we will take the second guy, and basically, what is this limit as epsilon goes to 0 and x is a real number here, right? Remember that this limit is evaluated inside the expectation. So here we just treat x as a real number, and so x is a real number. You multiply it by epsilon and magnitude epsilon, take limit as epsilon goes to 0. That's 0, and so this thing goes to 0, and the expectation 0 is 0. Right, and so yes, the limit of the upper bound on this thing goes to 0 as epsilon goes to infinity, and so we have this result here. The characteristic function is indeed differentiable, okay, and this is its first derivative. Okay, it is differentiable, and this is the first derivative, and if you evaluate the first derivative at 0, this is expectation e to the x e to the I to 0x, okay, and so e to the 0 is 1, so this is expectation ix, so this is I expectation x. Okay, so the first derivative evaluated at u equals 0 will give you the first moment, scaled now by I, okay, and in general, okay, this is the general theorem. If phi x of u is differentiable k times, then you can differentiate the characteristic function k times. This will be the kth derivative, and you can obtain the kth moment by basically putting u equals 0. Basically, the kth derivative at 0 is the kth moment multiplied by I to the k. Don't forget this I to the k. For the moment generating function, you don't have this scaling factor, but it is here, and of course, it is important to keep in mind. Okay, is there a converse? So what will be a converse for this theorem? So a converse for this theorem will be something like this. If the characteristic function is differentiable once, at ellipse once, then the first moment of the random variable is finite. Okay? So this will be the converse. So here we are saying that if the first moment is finite, the CF is differentiable once. So what about the converse? Is the converse true? Oh, not always true. So but we have a partial converse. Okay. So now let m be a positive integer. Now suppose that the derivative of order 2m. So here we are just talking about even orders of differentiation. If the even order of differentiation exists, then expectation x to the 2m is finite. Okay, so if phi x of 1 of u, so let's put this way, if phi x 1 of u exists, okay, can we say that expectation x is finite? No, because this is an odd power. Okay, so no. So if phi x of 2u exists, okay, then expectation x squared is finite? Yes. Okay, then Phi x is 3. Okay, no. Phi 4, yes. Okay, phi x4, fourth derivative, yes, and so on. So there is a partial converse, okay, and the derivation here, it requires something called the Fato's lemma. A Fato's lemma is like sort of a cousin for the dominated convergence theorem. We are not interested in the proof, but like basically the use of Fato's lemma is what imposes this pattern here. You know, it's basically applicable to things that are non-negative, and so basically when you raise real numbers to even powers, you are guaranteed to get something that is non-negative. So this converse will work only when those guys, the powers are even. Okay, so now central limit theorem, i.i.d. case. So here we are talking about the sum. So long, you know, I talked about this in the class. You know, I say the sum of random variables is an important thing. Okay, yes, it is important because it's used a lot. Like typically we do observations or measurements, and then we sum them, and then we scale them. Okay, so we scale them. So perhaps we sum them and that's it. Perhaps we sum them and divide by their number. Perhaps we sum them and divide by 1 over, you know, square root n, where n is their number, and so on and so forth. Okay, so now we are talking about basically what happens if you have i.i.d. random variables. Okay, so they are zero mean, and they have the same distribution as x. Okay, and we are interested in this quantity. Okay, so we sum the random variables x1 up to xn, and then we scale. So we divide by sigma, which is the standard deviation. So the assumption here is that our guys, they have a finite variance or finite second moment. And these things, as you can see in the previous slide, you know, these things are very important in theorems. You need to keep track of when the theorem is applicable and when it is not. Right? These theorems, they as you know, as the perhaps all theorems in mathematics, they come with conditions. Okay, so those conditions are not like trivial or not something to be ignored. So this theorem here will require that basically our random variables, they have finite second moments or finite variances. They are identically distributed, so all the guys, they have the same variance, which is sigma squared, and here we have sigma, the square root of sigma squared, or the so-called standard deviation. And then we scale by the square root of m. Okay, and then when we reach the chapter on the convergence of random variables, we will basically talk about the scaling by n itself. What if you take the sum and divide by n? But for now, we divide by the square root of n. So this is a random variable. Okay, it is the sum of n of those random variables. So here is a claim, and that's the central limit theorem, that as n gets very, very large, as n tends to infinity, then the CDF of this quantity here, it will converge to the CDF of a standard Gaussian random variable. Okay, so basically, if you have i.i.d., so let's see the conditions. i.i.d, okay, and finite second moment, and we take them to be zero mean. If they are not zero mean, then we need to subtract the means. Okay? If this is true, then the CDF of this quantity, as n gets very, very, very large, will converge. And it converge to the CDF of a standard Gaussian. You know, we know that the Q function is the complementary CDF, so 1 minus the Q function will basically be our limit. Now, if you use CDF, you know, the CDF is the integral of the BDF, and the BDF of the sum of two i.i.d. random variables will be a convolutional integral. If you sum three guys, then you will convolve the PDFs of, two BDFs and then convolve with the third, and it's very, very messy. Okay, so it does not make sense actually to basically to really work with the CDF and the BDFs if those guys are continuous random variables. So how can we do something? How can we deal with the sum in an efficient way? Characteristic function, right? Because characteristic function of a sum of independent random variables is a product of characteristic functions. No convolution, we just multiply. But the statement in the theorem is talking about a CDF, and now you are telling us, that we can use the characteristic function, but showing the convergence of the characteristic function. What does this tell us regarding the convergence of the CDF? It turns out there is a relation. Okay, so there is this thing here. We will take for granted the Levy's continuity theorem. It tells you, so basically in plain English, it tells you that, studying the characteristic function is as good as studying the CDF. So specifically, if a sequence of characteristic functions converge pointwise to a function, okay, you just need to check one thing, that the limit function is continuous at u equals 0. If this is the case, then the corresponding sequence of CDFs will converge to the corresponding CDF of the limit characteristic function. Again, the moral of the story is that you can solve problems regarding the convergence of CDFs using characteristic functions. You just have this condition that, you take the limit as we will do here. You just need to check that, the limit that you get is a continuous function at u equals 0, and that's it. Okay, so this is a friend, because again, dealing with sums of random variables using PMFs, PDFs, CDFs is very tough, perhaps impossible. Okay, so what is the way to go? CF. Okay, why not MGF? Why not the moment generating function? Well, it's like there are things like the Cauchy random variable, like in which, or other random variables like the log, let's not say Cauchy, let's say the log normal. The log normal, basically, it does not have a moment generating function that is basically, defined on positive t values. Okay, so but it has finite moments. But it has the log normal random variable. It has finite moments. So that so for moment generating function we have these restrictions. It is not always defined. It has a certain domain of t values. But the characteristic function is not like this. It's guaranteed to be finite for any type of random variable, right? So characteristic function, when you see sum, then a part of your brain should basically tell you CF, characteristic function. Okay, so this is something, keep in mind, we'll take it for granted and use it. And of course, this is a reminder that based on the previous slide, if we know that our random variables are basically they have finite second moments, then they are twice differentiable. And what will be the first derivative? So this guy will be expected x, and our guys are 0 mean, so this will be 0, and phi x2 of 0 will be I squared expected x. Okay, and so I squared is -1 squared, and because the random variables are 0 mean, then the second moment is the variance, and so this is -1 by sigma squared, and so this will be minus sigma squared. So basically this is an application of the previous result, that if the random variables, they have a finite kth moment, then the characteristic function can be differentiated k times, and you can obtain the moments from the characteristic function via differentiating k times, and basically you set u equal to 0. Okay, so we are ready to go. So we will use the characteristic function. Yes, the theorem is telling us about, talking about CDF, but we will use the characteristic function. okay, and this is the characteristic function of the sum of i.i.d. random variables. Because the guys are i.i.d., then the characteristic function, because they are independent, then the characteristic function of the sum is the is the product of characteristic functions. Because they are identically distributed, we can just take one characteristic function and raise it to the power n. Okay, so we can take the characteristic function of one of them, x over, this scaling parameter, and then we raise it to the power n. So because we have i.i.d. And that's, the beauty, no convolution. And then remember from the first slide, on characteristic function, phi a of x of u is phi of x of au, right? So it's proved that in basically 2 steps or something, 1 line. And so phi of x, and then it's multiplied by 1 over square root n sigma. Then we can take it inside. And so basically this is the characteristic function of the scaled sum. It's the sum divided by sigma and square root n. Take the logarithm of both sides, natural logarithm, so len and len. And then when you take the logarithm, of course, basically you have this n outside, and then you have the logarithm here. Okay? So what we will do is, basically, what we'll do here is replace n by 1 over alpha squared and investigate. So we need to investigate limit as n goes to infinity. Okay, and so n is 1 over alpha squared, so we'll basically investigate limit as alpha goes to 0. Okay, so this is what we will do. So here, this n becomes 1 over alpha squared, and this 1 over square root n becomes alpha, like this. Okay, so n, replace n by 1 over alpha squared, and then investigate this limit. Of course, when you investigate this limit, I mean, of course, there is always the possibility that actually the limit does not exist, right? So let's see. So what if you put alpha equals 0? In the denominator, you get a 0. What is the characteristic function of 0? What is the characteristic function of 0? What if you put u equals 0? 1, like the moment generating function. The moment generating function at t equals 0, the characteristic function at u equals 0, both are equal to 1. And what is the logarithm of 1? It's 0. So we are in a 0 by 0 situation. 0 over 0 situation. L'Hopital, we can apply L'Hopital, but if your functions are differentiable. Well, alpha squared is definitely differentiable. What about the logarithm of the characteristic function? Well, it's differentiable. Why? Why it's differentiable? Because of this. Because the second moment is finite, then this guy actually is twice differentiable. So see why these assumptions are very important. Without them, you cannot, if we don't make an assumption regarding the moments whatsoever, then we are not even sure that the characteristic function is differentiable, right? And so basically we will be stuck here. But now, because we know that the characteristic function is differentiable, we can proceed by L'Hopital, and we can differentiate the numerator and the denominator. So alpha squared becomes 2 alpha. So what is the derivative with respect to alpha of len phi x of alpha u over sigma? Okay, so chain rule, so basically len something, so you basically get the thing in the denominator, but then you need to apply the chain rule, so you need to differentiate the thing inside the logarithm. Okay, and it is differentiable because the random variable has a finite second moment, so actually the characteristic function is twice differentiable. Okay, so these are basically the derivatives. And now, what if alpha is 0? Now, if alpha is 0, this is 1. Now, if alpha is 0, we still have we have alpha in the denominator, so 0. And what about the numerator? In the numerator, we will have the first derivative of the characteristic function evaluated at 0. This actually is proportional to the first moment, and those guys are 0 mean, so this is 0. So again, a 0 over 0 situation. L'Hopital is applicable again because the characteristic function is twice differentiable. So we can apply L'Hopital again. And now we will get this alpha now is gone because the derivative of alpha with respect to alpha is 1, and the first, and the first guy. Of course, here when you differentiate this, there is by the chain rule, of course, you are differentiating with respect to alpha, you will get u over sigma outside. It's like a constant multiplied by alpha. And when you differentiate again, you will get u over sigma again, and so you will get u squared over sigma squared, and then you will get the second derivative of the characteristic function evaluated at 0, and by our previous theorem, this is minus sigma squared. Okay, and so it's minus u squared over. So if we study this limit with the continuous parameter alpha, the limit exists and it is actually equal to minus u squared over 2. But remember, our original limit is actually the limit with this n goes to infinity. So by Hein's definition of the limit, so Hein basically his definition of the limit is that if you have a continuous variable like this and the limit exists, then if you replace the continuous variable by any sequence going to that limit, then the limit holds. Okay, so alpha tends to 0. Now replace alpha by 1 over square root n, right? So it will basically go to the same limit, which is minus u squared over 2. Now, especially those guys like in engineering, like if they have something that looks like this, they can work with it. Why did I go from u to alpha? It's because like if you want to apply L'Hopital, well, n is an integer, right? So how can you differentiate with respect to n? So if you want to be rigorous, this is the way to go, is basically to replace with a continuous variable and then to use Hein's definition of the limit. Okay, but if you operate with L'Hopital on this thing directly, this will be sort of not a problem in this course. If this is, it is not technically correct. Again, you say, okay, here, if you operate on this guy, say, okay, it's infinity multiplied by 0. We need to apply L'Hopital, so let's differentiate with respect to n. But n is an integer, right? So again, so this is sort of a technical thing to do things in a in the correct way, sort of speaking, but it's not essential. I mean, so basically in our course here, I will focus mainly on getting the limit correctly. You need to get the limit correctly. Okay, so this is the most important thing. So this thing here, as n goes to infinity, it goes to minus u squared over 2, and because the exponential is a continuous function, then the limit of phi of epsilon and u is basically e to the minus u squared over n. And what about this function? Is this function continuous at u equals 0? Yes. I mean, this function you can plot. It looks something. It's basically something that looks like this, and it is actually this function is not just continuous; it is infinitely differentiable. And so we can apply now continuity, Levi continuity, which means that basically if your characteristic functions converge to something that is continuous at u equals 0, then actually the CDFs converge. Okay, so this statement will hold, and the CDF of epsilon n will converge to the CDF of what? The CDF of what? So basically, what is this thing? Okay, so what is e to the minus u squared over 2? It is the CF of the normal 0, 1 random variable. Okay, so basically the Gaussian random variable, it has a very nice characteristic function, and basically the characteristic function, if x is, this is one thing that, if x is let's say the mean value, if x is eta sigma squared, then basically the characteristic function, okay, is e to the I u eta minus half sigma squared u squared. And so basically if the random variable is Gaussian, is 0 mean, and if the variance is equal to 1, then the characteristic function becomes this nice e to the minus half u squared. Okay, so so again, like the characteristic function of the Gaussian random variable is very important. It is obtained by basically applying the definition of the characteristic function and doing a contour integration in the complex plane. Again, we don't need to know how it is derived. You can take it as a starting point. It's very, very important, and it's in the cheat sheet and in all references of your choice, the characteristic function of the Gaussian random variable, and in the special case when it is zero mean and unit variance. Okay, so the characteristic function here goes to this guy, and you say, okay, then what? Well, this guy, e to the minus u squared over 2, is indeed the characteristic function of a standard Gaussian random variable, which is Gaussian with zero mean and unit variance. So it means that the sequence of CDFs will converge to the CDF of a standard Gaussian random variable, and we know that the Q function is the complementary CDF, so basically we will converge to 1 minus Q of y, where Q is the Q function. Okay, so so this is the central limit theorem. I will tell you that this proof is very, very important. You know, you need, like, because you know the idea is here, the idea of writing the characteristic function of a sum, you know, and then exploiting things like independence or perhaps i.i.d, then taking limit, and you know sometimes this will involve a L'Hopital. And as I said, I don't care how you apply L'Hopital. You know, if you use like to apply it even to variables that are integers, well, you know, it does not look okay, but it is. I mean, if you get your limit correctly, I am fine. Okay, so so basically this is a very important proof, and it is a very important result in probability and statistics. If you have, and it tells you why Gaussian is like important. The Gaussian random variables, why it's important, why it's sometimes called the normal distribution. It's because of this. But if you take, I mean, did we say anything regarding the distribution of the x's? Nothing, right? Nothing. We didn't say anything about the x's, right? They are just zero mean. They are just zero mean, and they have a finite second moment. Okay, they are i.i.d. They are zero mean. They have a finite second moment. Okay, this is what is needed. So what will happen if you sum n of those guys, divide by sigma, divide by the square root of n? Then, you know, basically this is a random variable. You know, this is a random variable that gets closer and closer and closer to the standard Gaussian random variable, right? So that's the reason. So basically you start with any distribution, so long as it's a finite second moment, and so long as your guys are i.i.d, then you converge to a specific distribution, which is the Gaussian distribution. Okay, so that's the reason. Like, you know, it is like, so it appears like, so if you have a phenomena that basically that is sort of summing a big bunch, you know, a large number of random variables with finite second moments, then you will find, you know, the Gaussian distribution emerging basically from whatever, you know, from this system. So so this is the central limit theorem, and basically again, if you know expectation xk is equal to eta, then basically you define psi n as 1 over square root n sigma. So what will converge will basically be xk, and you subtract the mean. So we said that the mean is subtract the mean. Okay. So if your stuff is so basically this zero mean business is not like sort of essential. You know, you basically, if they do not have a mean of 0, then you work with the random variables from which the first moment is finite, and so this guy is 0 mean. Okay, so xk minus eta will be 0 mean. Okay. Now there are so many central limit theorems. It's not just one central limit theorem. Okay, there are several central limit theorems. Okay, so here we will just focus on another one, and it's the Lyapunov central limit theorem. So the Lyapunov central limit theorem, we will keep the assumption of independence, but now we will allow our variables basically to have basically different basically statistics, perhaps different distributions. Okay, so it's non-identically distributed case. Okay, so now our guys, let x1, x2 till xn, then those guys are independent. Okay, I mean, without independence, things will be tough. So independence, they're zero mean, not a biggie. They have a variance. Now, the variance is finite, but now, as you can see, the variance now is sigma k squared. Okay, sigma k squared. So each guy may have its own variance because they are not necessarily identically. You know, they don't have the same distribution, right? Now, to have convergence in this case, things are a bit different. We need a stronger condition than just the second moment being finite. Okay, so in the i.i.d. case, we need expectation, you know, of x1 squared, you know, and those guys, you know, xk squared, those should be, you know, finite. Now here, okay, for the Lyapunov CLT, we need expectation xk to the power 2 plus something. We need to go higher than basically the second moment. We need this thing with the delta, and delta is, you know, between 0 and 1. We typically, or let's not say typically, we sometimes just use delta equals 1. But I mean, it's not necessary. So delta can be any number, you know, strictly greater than 0, 1. We need this guy to be finite. Okay. Why? Because to prove, so it's a nice question, because like in the previous case, why did we insist that the variance is finite? So suppose that you start your theorem like just playing with the characteristic function. But then you have a limit, and then you have to evaluate it, and then you are stuck in a 0 over 0 situation, and then you say, oh, I need L'Hopital, but to apply L'Hopital, I need differentiability. Oh, I need actually to apply L'Hopital twice, so I need twice differentiability. So how can I guarantee that actually we have twice differentiability? So it must be the case that the second moment or the variance is finite. Same story here. So there are these things that you will not be able to see except by diving into the proof. Okay, so in the proof, it will be clear why actually we need something like this. Without this thing, you know, so again, like when you see the theorem, typically you see these conditions first, and they look mysterious. Okay, but when you do the proof, you know, that's actually one of the big advantages of knowing the proof. Is like, now, you know, you will see why this is needed. Definitely, there will be a limit, and we will try to evaluate that limit, and we will be stuck unless we assume that something is finite. Okay? But actually, in our case here for the Lyapunov CLT, there is more. So we will require that this is finite for every k, but we also require something that looks bizarre, looks a bit weird, which is this limit here should be 0. So let's try to understand what this thing is. Okay, so this thing is the form. So it is a summation. So it's not just that we need this expectation to be finite. If we take the sum of those guys to the plus delta, and we sum from 1 to n, and then we divide by Sn to the power 2 plus delta. Sn to the power 2 plus delta, okay? So what is Sn? So we need something here, 2 plus delta. What is this Sn? This Sn is basically the square root of summation k from 1 to n, sigma k squared. So basically, Sn is the square root of the sum of variances. And again, those guys, may be different from one another because it's not, we are in a situation in which the guys are non-identically distributed, right? So this is a quantity, okay? This is a quantity. And for the theorem to work, we will need the limit of this thing as n goes to infinity to be 0. Not intuitive, actually, what this thing is. But you can make a guess right now, right? It will be something that we encounter in the proof. Okay, so we will see this, and we have a limit, and we want the limit to go to 0, and then we say, okay, so what? So there is a condition in the theorem. We want this guy to basically, this limit to be 0, so that our result is guaranteed. Okay, so here again things are a bit more complicated. We want basically something a bit higher than the second moment to be finite. A bit higher than the second moment to be finite. So that's number one. And it's not the end of the story. We want this monster here to basically to go to 0 as limit n goes to infinity. If this is true, then basically this quantity will converge, the CDF of this quantity will converge to the CDF of a standard Gaussian random variable. So note now that in the i.i.d. case, we have summation x from 1 to n xk. Remember what we have outside, 1 over square root n sigma. Here what we have is summation k from 1 to n xk, and then we have Sn in the denominator. What is Sn? It is 1 over square root summation k from 1 to n sigma k squared. So this is the scaling. Yeah. You can, I mean, for the moment, this is basically, you can, so basically have something like this, b equals 2.7311. Yeah, it's okay. Why not? It may be difficult to compute. Maybe if these random variables are continuous and you write down the integral, it may not be something that you can evaluate. But why not? I mean, right? So you can take the magnitude to the power b. B, I mean, is not necessarily n. So in practice, we typically use like those, integer orders for moments, but it's not necessarily, you can basically define this thing to be any number of your choice. So here, basically, if you want to work with integers, this will be the case in which you choose delta to be 1. And again, sometimes we just do this. We just put delta equals 1, and basically our stuff will involve the third absolute moment. But it's not necessary. We just need it that it is strictly greater than 0, but is less than or equal to 1. Okay? So this is what converges. Now, if basically our guys are not 0 mean, then the theorem is applicable by replacing each random variable by the random. So you replace, so if xk is not 0 mean, replace xk by xk minus its first moment. Okay, and so this work with this guy, which is 0. Okay, so it's, being non-zero mean is not a biggie. Okay, but the other conditions are sort of extremely important. Independence, of course, and we need basically this a bit higher than the second moment to be finite, and then we want this guy here to have a limit of 0 as n goes to infinity. Okay, so so basically one of those limits is you did it in a homework problem. We don't, I think, have time like to go through the full proof. So what I will do is like I will give you the outline. So what's the idea? And then we will do the detailed proof in the next lecture. Okay? So here's the idea, the game plan. Okay, game plan. Okay, so we have hopes. We want also like to have this type of convergence to, the convergence of the CDFs. So we want the CDF of this quantity here to converge to the CDF of a standard Gaussian. But we learned that we can work with characteristic functions. Okay, so what we will do is that we will take the characteristic function of this quantity. Don't forget that Sn is the square root of sigma 1 squared plus sigma 2 squared up to sigma n squared. So we'll take the characteristic function of this quantity. Okay, no problem if we take the logarithm. It's actually here log, it means len. Okay, so it is len. And then, so this will be the logarithm of the characteristic function of our quantity. Hopefully, if n becomes very, very large, basically this thing approaches the logarithm of the CF of n01 random variable. The standard Gaussian random variable, what is the CF? Is e to the minus u squared over 2. So if we apply logarithm, this will be minus u squared over 2. Okay, so this is the minus u squared over 2, and this is the logarithm. Okay, so what do you think will be the plan? The plan is we will take this quantity. Okay, we'll take this quantity, and we will take this quantity, which is again the logarithm of the characteristic function of a standard Gaussian. We will take the difference, and we will try to show that the magnitude of the difference as n goes to infinity is 0. Okay, so we want to show convergence. Okay, and those, this thing can be, complex valued, no problem. So what we will do is that we will try to show that the magnitude of the difference actually goes to 0 as n goes to infinity. And if this is true, then basically the limit, I will just say it, if you take the limit n goes to infinity of magnitude gamma is 0, then limit n goes to infinity of gamma itself is 0, then basically the limit of this quantity here is equal to 0, that's gamma, and so this limit is equal to e to the minus u squared over 2. But if you have a limit, you can take the exponential of both sides because the exponential is a continuous function. So let's again write this. So limit n goes to infinity, gamma is 0. Then limit n goes to infinity of gamma is 0. Then limit, what is gamma? It is the logarithm of phi 1 over Sn summation xk of u minus u squared over 2 is 0. Then limit n goes to infinity of log phi 1 over Sn summation xk of u equals, move this to the other side, minus u squared over 2. Then exponentiate both sides, and this is valid because basically exponential is continuous function, is a continuous function. Then what you can do is that you can say that the limit as n goes to infinity of this thing 1 over Sn summation xk of u is e to the minus u squared over 2, which again is the CF of normal 0. Okay, so that's the plan. Okay, of course the challenge will be well, this one. This will be the challenge. And how can we show? I mean, once we are done, that's it. I mean, basically, then we have our result. But how can we show this? So again, like in a previous proof in this lecture, we will not basically get to this limit directly. So here, for here, we use the sandwich theorem, which means that we will not basically deal with this limit, of this quantity exactly. What we will try to do is that we will try to upper bound it, and then we will show that the upper bound goes to 0. Okay, and so by the sandwich theorem, then this limit is 0, and then we have basically our result. So the challenge will be the upper bounding, and this is what we will do in the coming lecture. So basically, how can we upper bound and then show that the upper bound is 0? Just the last thing to show you is that when you do the upper bound, you will get, for example, something like this. Okay, and how how do you show that that basically that this thing goes to 0 as n goes to infinity? You cannot do it. You just assume it. Okay, you just assume it, and it becomes a condition in the theorem.